So the first talk, we have two talks. The first talk of the session is Deletions and Dishonesty, Probabilistic Data Structures in Adversarial Settings by Mia Filic, Karen Kocher, Ella Kamar, and Anupama Unnikrishnan. And Mia will be giving the talk. So.
Thank you very much. Yes, my name is Mia. I'm at ETH still. I work with also Kenny Patterson, but this work was done jointly with other people, with two of my master students, Karen Kocher and Ella Kumar, and my colleague Anupama Unnikrishnan. So as you said, we studied probabilistic data structures in adversarial settings, and we focused on the ones with deletions. So let us see what we did on that topic. First, in general, what are those PDSs? Well, they present a way how to very compactly represent tons of data, and then to use only that compact representation to provide us with answers to queries, but only in an approximate way about the data stored. Now, depending on the type of the queries that specific probabilistic data structure answers, we can have frequency estimation PDSs such as counting sketches and heavy keeper, then also membership query PDSs, examples, Bloom filter, Cuckoo filter, counting filter, then also, for example, cardinality estimation PDSs. We use those data structure when we, for example, want to do cache summarization for content routing, then possibly to also identify denial of service threats within network monitoring systems, then for certificate revocation checking, or to just count number of distinct users of a certain system. Okay, so we have probabilistic data structure. They are used in practice. All should be good, right? What am I doing here? Well, actually, those PDSs, their guarantees, their probabilistic guarantees are usually only proven in honest settings. You can think about these honest settings as something as average case scenario or something like that. But we find that these are also used in settings where there is no direct enforcement on the parties within the system to actually behave honestly. So then we ask ourselves, okay, this hasn't been studied. Can something go wrong in adversarial settings? Or are those correctness guarantees from honest setting also valid in adversarial setting? Just no one made the effort to actually prove that. So then in these adversarial settings, we focused on adversarial correctness of PDSs, or can some adversary interfere with the correct functionality of the PDS? But we can also consider ourselves with privacy of PDSs, where, for example, adversary could try to learn something about the elements actually represented by the PDS. We don't address this privacy concern in this paper. There are some papers who did start on that for different type of PDSs and also for MQ-PDSs or membership, approximate membership query PDSs with deletions. We're going to leave that for future work. Now, okay, we focus on adversarial correctness, and then not only that we try to see, okay, how adversary can interfere with the functionality of the PDS, but also then we take a step further and want to see if there is a way that we can provably protect our PDSs in those settings. This is quite a big topic, so that's why the title of my paper, of our paper, which kind of narrows this down to a certain class of MQ-PDSs with deletions, for example, counting and Cuckoo filters. For the rest, I will mainly focus on a counting filter example. So some of the motivation, some of our results, I'm gonna give through the lens of counting filters, and for some other examples of our focus PDS class, you can just go online and read our paper. So what counting filters actually are, for some of you who never heard of counting filters or PDSs in general, well, internally, counting filter is just like one long vector of counters, and at the start of their lifetime, we have that all those counters are actually set to 0. Our counting filter also have k-independent hash functions that it's associated to, and those k-independent hash functions associate certain elements with specific set of counters within that vector. I'm just writing here just one hash call just for the compactness of the slides. It should be k different hash functions. Now, how do we use this counting filter? Well, if you want to insert elements, you just give your element to the counting filter, and then counting filter first passes that through k-independent hash functions, obtaining the associated counters, and then those counters are incremented by 1. Then you can just keep inserting other elements, incremented counters associated with new elements, up until some max count value is reached, and then whichever insertion was about to go beyond that value, that insertion gets rejected. If you want to delete elements, then you just revert the insertion process, subtracting something from the counters of your element that you are deleting. Querying elements happen similarly. So first, the element you are querying goes through k-independent hash functions, obtaining associated counters, and then those counters are checked if greater than 0. If they are, you obtain positive answer. Otherwise, you just get a negative answer. If you remember from my first slide, you can issue queries to your PDSs. However, you are only getting approximate answers. Now, what does that mean for the case of counting filters? Well, you can have false positive answers and false negative answers. In the honest setting, the probabilities for getting a false positive or false negative answer is usually very well characterized, not only for counting filters, but also for AMQ PDSs in general. And we have that a false positive probability is usually upbounded by some function which depends on the public parameters of our filter, but also the number of elements that are currently stored in the filter. And for false negatives, they're often just assumed not to occur under honest settings. Now, under adversary, what can happen? Let us motivate that by one example. Let us take one adversarial user, and that user, as every other user in the system, has API access to our counting filter. They can insert, query, or delete elements in whichever order they want. But also, in addition to that, they also have direct access to underlying hash functions. Why? Because in implementation, actual implementations in library, what we often see is that the hash functions associated with PDSs are just instantiated as public hash functions. Now, when I say public hash functions, people should think pre-computation attacks. Yes, that's correct. Adversary can use hash pre-computations to their advantage to violate correctness of the PDSs in adversarial settings. One example Let us take that our adversary just wants to make some target W a false positive. Now, using pre-computations, it first does hashes W, then it continuously hashes other elements until they find a set of elements such that when you insert that set of elements, you increment all W's counters, which then yields that whoever later on going to query W will get a positive answer, even though maybe W was never inserted into our PDS. And this way of inserting elements is adaptive, so it's not something that you assume going to happen in honest settings. There are also other things that can go wrong with counting filters, but also with some other PDSs. For example, for counting sketch, you can cause frequencies of a certain element to be unexpectedly overestimated. Now, do we want to secure our PDSs? Of course, we want to at least try on that. First idea to that is, okay, we have these public hash functions. What happens if we simply use some cryptographic tools here instead? For example, keyed PRFs. What do we get there? Okay, we stop recomputations on hash functions, but do we stop all sorts of adaptive attacks? Unfortunately not, because adversary can still take advantage of learning something from previous insertions, queries, or deletions, and then later on adaptively make new insertions, queries, and deletions. But in this setting, what at least we get that we can quantify the level of security for our PDS. So then we went down that line. We replaced public hashes with PRFs, and now we want to quantify adversarial correctness for our class of PDS. In past, people did that already for different PDSs or in different ways that we are doing. For example, using game-based notions, starting by Nauer Yogev 2015, Clayton and al. 2019. And those game-based notions give you some bounds on correctness guarantees in adversarial settings. And the proofs, a lot of proofs are involved, but also specific to certain adversarial goals and PDSs that were analyzed. Then later on, other people and also myself in 2022, we decided to use simulation-based notions to quantify this security of PDSs. Why? Because with those notions, we managed to generalize more our results to be applicable to a certain class of PDSs and also to more adversarial goals more easily. So in this work, as you expect, simulation-based framework going to be used. And now just a short recap what that is. In this framework, we have two worlds, real world, ideal world. And for our case, in real world, we have adversary interacting with a concrete instantiation of our PDS. And then in ideal world, we have adversary interacting with a simulator. For our AM2 PDSs or PDSs in general, what do you then want to do with our simulator is to create it in certain way such that they provide an honest view of the PDS to the adversary. Why that? Because then we can already use some results from PDS literature to analyze our ideal world, which is great. More details on how we defined our simulator can be found in our paper. Now, next, okay, now we have our framework, we have our simulator. Next, we upper bound the difference between the two worlds. For our class of MP PDSs, we obtained the following bound, which here contains one term depending on maximal false positive probability given certain number of insertions that we expect to happen times this function of the number of different oracle calls can be insertions queries deletion plus insertion failure probability term and this PRF advantage term. For our focus PDSs, we found that this term is not asymptotic, so there are results that are not asymptotic, which is great because even though this term is not negligible in usual cryptographic sense, we can use it to say something useful. So we have our term. Now, next step is let us see how we can derive bounds on adversarial correctness for our PDSs from here. First, observe that now probability of an adversary to achieve any adversarial goal in real world is upper bounded by the probability of adversary achieving the same goal in the ideal world plus this additional term. In the case of MQ PDSs, usually you focus on false positive probability, and then first you set up an upper bound on the false positive probability, and then in some sense you reverse engineer what's going to be the sizes of your filter such that that upper bound is never exceeded. So we do that now also for our adversarial setting by first modeling specific adversarial goal to be exactly this false positive probability. And now in ideal world, we know how to upper bound this false positive probability from PDS literature, which is good, obtaining this term over here that we have on the right-hand side. And then from there, we can derive parameters of our counting filter or like certain class of MQ PDSs. For counting filters, how do we derive those parameters? Is, for example, what do we do? Okay, we first, I mean, it doesn't have to be actually in this order. This is just one example in which we first set the max count value to a certain value, which is 15. Why 15? Because in practice, we saw that 15 is often used. Then we also need to make the number, make a decision on the upper bound of the number of queries that our users going to be doing towards our counting filter. In this case, I set it to 2 to the 20 insertions, deletions, and queries, 2 to the 20 each, I mean. And then we see on this figure 4 different lines, each line corresponding to one value of k. K is that number of k-independent hash functions. And now from there, for example, you target here, what's usual false positive probability one target is, for example, 0.01, which is around here minus 6.6. Then we get what are the points over here on our lines corresponding to this false positive probability. And then we look to the x-axis of those points to actually get the absolute size of our vector of counters that our counting filter needs to have to achieve this level of adversarial correctness. So here we have here 8.5, I guess, for k equals 24. Okay, those lines, I forgot to mention, those lines are first for the honest setting scenario. Now, when we move to adversarial setting, we are getting slightly different lines, more on the right here, which is, I guess, what we expect. And now how to derive parameters for our counting filter in adversarial setting is, okay, now we just continue this line here and take x-axis from here, getting us to 22.5, I think, or somewhere around that, which then implies that switching from honest setting to adversarial setting to have the same correctness guarantee, you need to, I guess it's not actually triple the size of the vector, but it's definitely bigger than doubling, so within doubling and tripling it. If you disallow deletions, you can fine-tune even better your size. More on that can be found in our paper. Final remarks. So good timing. What maybe was not explicit up to this point is that, you know, I said that honest setting simulator needs to emulate honest setting. Well, to know what we need to emulate, actually, we needed to formalize first what the honest setting means. What is this honest view for MQPDSs? And we found out that it actually differs from the one for the insertion only case. So insertion only membership query PDSs. We found out that deletions enhance adversarial power, but with proper parameter selection, we can still achieve claim correctness guarantees. Future works, analyze privacy of MQPDSs with deletions, analyze other PDSs, and my top favorite for now, in our work, we were considering ourselves with malicious users interacting with the server that is giving you the answers to your queries, to your insertions, deletions, and queries. Now, what happens if the server is now malicious? Can we guarantee something for our honest users or nothing? And full disclaimer, we are actually working on this, hoping to fine-tune the final things soon. So stay tuned for new papers coming up. Thank you very much.
Thank you. We have time for a quick question, if anyone has one. No?
It can be also an obvious question. Probably I missed to mention some things because, yeah, when you are presenting live.
Right. If not, let's thank Mia again and let's move to the next talk of the session.
Good.
The last talk of the session is concurrent encrypted multi-maps by Archita Agarwal, Seni Kamara, and Tariq Motas. And Archita will give the talk. It's an online talk.
Nishan, should I go ahead and just share my screen?
Yes. Yes, please. Yeah, we can see a screen. Maybe you can make it full screen.
Oh, okay. Can you see my slides now?
Yes, it's good. Thank you.
And can you see my pointer? Just checking.
Yes. Yes.
Okay, thank you. Okay, yeah, hi everyone. I'll present our work on concurrent encrypted multimaps, and this is joint work with Seni Kamara and Tariq Motas. So let's quickly review what are multimaps before we see what are encrypted multimaps. So multimaps are a type of data structures and they map labels to a tuple of values. So for example, for instance, in this example, L1 is mapped to a tuple of V1, V2, and V3. L2 is mapped to V1 and V2, and so on and so forth. Right, and these multi-maps, they support operations to read and write to these label value tuples. For example, we can get the tuple associated with a label L, we can add a value to the tuple of L, and so on. Now, encrypted multimaps, they are just encrypted counterparts of plain text multimaps. These multimaps, encrypted versions, they encrypt the plain text multimaps data structure in such a way that now you can do the same operations but on encrypted data. Now, the way you construct these encrypted multimaps differs from construction to construction, but the idea is that they just allow us to do the same set of operations but on encrypted data. And these encrypted data structures are really useful in cloud settings where, let's say, a user Alice can first encrypt her data in a multimap and then upload it to an untrusted cloud. And since the data is encrypted at all times, the server does not learn anything about her data or the operations that she performs on her data structure. So these encrypted multimaps, they have been heavily studied since early 2000s, where people have studied them along several dimensions, for example, for their page efficiency, IO efficiency, or improving their leakages. People have also studied lower bounds on them. But unfortunately, none of these works, they consider the multimaps to support concurrent operations. So what does that mean? They assume that the server is sequential. It will execute operations one after the other. So the first operation gets executed, then the second operation gets executed, and so on. This is, of course, not great because modern server architectures, they are not really sequential. They're powerful machines which are capable of executing multiple operations simultaneously. So in this work, we actually initiate the study of concurrent encrypted data structures and multimaps in particular. So there are many questions that come up when we start studying concurrent encrypted data structures. Of course, there are design questions that how do you design these things? But there are other foundational questions. For example, how do you model, first of all, these multi-threaded or these concurrent machines? So let's just start with that and then we will see other ones. Okay, so in the sequential setting, not in the concurrent setting, we assume that server has a CPU, it has memory for storing data. When an operation comes in, the CPU will execute all the instructions one by one that compose this operation. And once all the instructions are completed, then maybe the server gets the second operation, then it does the same thing with the second operation. Right? However, in the concurrent setting, there can be multiple operations that the server receives simultaneously. So what we assume that in addition to this, to the server having a CPU and this shared memory, there is this additional entity that we call as a scheduler, which is now responsible for deciding how the instructions of these operations will be executed by the CPU. So maybe the scheduler first runs some instructions of OP1, then it pauses OP1, then it moves on to OP2, does some instructions of OP2, pauses it, maybe resumes OP1, and so on and so forth. Right? So because we have this scheduler, we model this concurrency using the scheduler, we see that this captures the asynchronous nature of modern architectures because now the scheduler is free to choose any possible interleaving of the instructions, which is essentially what asynchronicity gives us. So that's how we modeled multi-threaded architectures. Now let's see who our adversary is. So we assume the server where the adversary is sitting to be persistent and semi-honest. This is like standard for cryptography. But we also assume that the adversary now controls the scheduler. And this allows us to study the security of EMMs or encrypted multimaps for all possible execution schedules that can occur at the server. For correctness, what we mean is that given an operation, what should be its output, right? And in the sequential setting, this is pretty obvious that how do you define correctness? So if you have two operations, let's say append followed by a get, then we know that the get operation will see what append did. So if append added a value v5 to L2, then v5 will be present in the output of get of L2. However, in the concurrent setting, let's say if these two operations occur concurrently, then there are two possible outputs for get of L2. One where V5 is in the output of get and one where it is not. And out of the two possibilities, the one which actually gets output depends on how the scheduler interleaved the instructions of these two operations. Okay. So to define correctness of these concurrent data structures, we borrow the notion of consistency guarantees from distributed systems literature. And there are various consistency guarantees that are defined in the literature. Some are stronger, some are weaker. The difference is just that the stronger ones allow for less number of possible outputs for an operation, whereas the weaker ones allow for more number of possible outputs. So in some sense, like stronger consistency guarantees are more deterministic than the weaker ones. So that's how we defined correctness using consistency notions. And finally, let's look at how do we define security of concurrent encrypted data structures. So we formalize security in the real and ideal paradigm. One thing, however, we notice is that the outputs for each operation, they now depend on the consistency that the concurrent data structure is offering. And even if you fix the consistency guarantee, let's say linearizability, then also an operation can have multiple valid outputs and the scheduler chooses which of all possible ones actually gets output for an operation. So to capture this fact, what we do is that in the ideal world, we now allow the simulator who's simulating the scheduler to impact the outputs of an operation. So it sends some scheduling information to the ideal functionality based on which the answer for an operation is generated. So there are many subtleties that come up, and please refer to our paper for more details. Okay, so that's how we define security. And now let's come to the design part, that how do we design now a concurrent encrypted multimap scheme. First, let's look at the design goals. So with respect to consistency guarantee, we aim to achieve linearizability, which is a very, very strong notion of consistency and is also a standard in concurrent systems literature. So linearizability states that every operation, because there can be multiple concurrent operations happening, so every operation should appear to take place atomically and in some order. And moreover, that order should be consistent with the real-time ordering of those operations. Meaning that if, let's say, we have two operations OP3 and OP6, where OP3 finished before OP6 started, then we should be ordering OP3 before OP6. And ordering OP6 before OP3 is wrong. Linearizability doesn't allow for that. So linearizability respects this real-time ordering of operations. And in terms of security, we aim for forward privacy. This is again a standard of security for EMMs in the sequential setting. And forward privacy states that update operations, they cannot be linked. So if you're appending, which is an update operation, they cannot be linked to previous search operations. And finally, in terms of efficiency, we try we try to be as efficient as possible. We try for log freedom, which means that we do not use logs. But if we do use logs, we try to be as fine-grained as possible. And in addition to all these, we also try to avoid any intra-client communication in our protocol, because this is just unrealistic to have clients talking to each other in the real world. So given these design goals, let's see how TST works. We will first see how TST works in plain text, and then we'll try to encrypt things to make everything secure. Okay. So for each client and for each label in TST, we store a separate linked list at the server. So for example, if there are two labels L1 and L2 and two clients C1 and C2, then for client C1, we store two lists, one for L1, one for L2. Similarly, for C2, we have two lists. Moreover, in the pictures that I'll show you from now on, everything on the right of the pink line is happening server side, and everything on the left is happening client side. Okay, so now if CI adds values, let's say V1, V2, V15 to label L1, then those values are stored in list I of L1. Whereas if client CJ adds, let's say V5 and V3 to L1, these are stored in this list. And the heads of these lists, these linked lists, they are stored in separate dictionaries, and we call the heads as checkpoints. So for instance, if the address of this node, which is the head node, is R113, then checkpoint of I of L1 is R113. Similarly, checkpoint of J of L1 is R212. Okay, then let's see how append gets work. To append, let's say value V17 to L1, we simply add a node to this linked list and update the checkpoint. Then on a get, we simply read all the nodes that are reachable from the checkpoints in L1 list. So we read both L1 lists starting from the checkpoints and retrieve the values stored in those nodes. However, this simple scheme that I just described, where adding to a linked list or reading these linked lists, this is not forward private. And this is because that both adds and appends and get operations, they read and write the same checkpoint, which reveal correlations between those two operations to the server, violating forward privacy. So to make this forward private, we do not update the checkpoints at append time, sorry. So at append time, we simply add a node, but do not update the checkpoint. However, this breaks linearizability, because now there are some nodes which are not retrieved at get time, because at get time, we just traverse the list starting from this checkpoint, so this is missed. So somehow we want get operations to retrieve nodes which are unreachable through the checkpoints. So to do this, what we do is that we store a strictly increasing atomic counter at the server. And every append operation uses the current counter value, whatever the counter value is at that point of time, to stamp the node that it is adding to the list. So now every node has a value and a counter value stored in it. And then get operation uses this counter value to retrieve the unreachable nodes. How? So if the ith checkpoint node, let's say, has a counter value of C, then we retrieve all the nodes from the client that has counter greater than C. So for example, in this list, the checkpoint node has counter of 6, so we retrieve all the nodes that have counters greater than 6, which is this node, right? 10 is greater than 6. Similarly, in this case, the checkpoint node has counter of 7, so we retrieve all the nodes from Cj that has counter greater than 7. So these three nodes. So as you can see that this step actually retrieves these unreachable nodes, but also retrieves something extra. For example, we retrieve some L2 nodes as well, which we did not want, but the client can simply filter these out on its own using the label information that we can additionally store in these nodes. Right, and after filtering, at get time, the client updates the checkpoint. So we are no longer updating checkpoints at append time, but at get time. So let me just combine everything for you. So to append a value to a label, the client first of all sends a node, the server stamps the node and adds it to the right list. Then to get the tuple, it traverses all the L1 nodes, starting from their respective checkpoints, does the counter business that I described earlier to retrieve some extra nodes. This ensures that all the unreachable nodes are retrieved. The client then filters out the false positives using the label information stored in the nodes and finally updates the checkpoints. So this is at a high level how TST works. Unfortunately, this is still not linearizable and there are some race conditions that can occur during this protocol, and I'm not going to describe these race conditions. Please read our paper. But the point is that to avoid these race conditions, we have to do extra synchronization. We use like hand over hand locking. We also do some filtering based on counter values, but you can see our paper that how we do that. In the end, we show that if these underlying data structures are linearizable, then TST is linearizable. And now let's see that how we can add encryption to these data structures to make TST secure, where secure is how we defined it earlier. Okay, so here we have two lists, two clients, and each has one list. There can be other lists as well, but here I just showed you L1 list. So first thing to notice is that these arrows here, they are just representational. An arrow from this node to this node really means that this node stores this address of this previous node in itself, right? So if R112 is the address of this node, then an arrow from R113 to this node just means that R112 is stored here. Okay, so now given these lists, what we want to do is that we want to encrypt them somehow, right? And notice that in each node, there are two kinds of data. One that the server needs to know because it wants to do the traversal, and one which it doesn't need to know because that data is just there for clients to use. For instance, the values and the labels, they are just there for the client to maybe do filtering, right? So the part that the server doesn't need to know, we encrypt it under the shared key and have all the clients share that key. For example, pink key maybe. But we cannot do the same with these back addresses. There are two problems with this because we need to know how and where do we decrypt then these addresses for the server, because server needs to know these addresses for traversal purposes. Right, so one way would be to give the blue key to the server, but and let the server decrypt these, but this would break forward privacy because once the server has the blue key, then it can just decrypt all the future nodes as well. Then why are we even decrypting? Why are we even encrypting? And the second option then will be that we do not give, of course, the server this blue key and let these be decrypted client side. However, this is super inefficient because for each node that the server wants to decrypt, it needs to talk to the clients. So what we do instead is that we use the idea of chaining, and what we each node then is encrypted under a new key, and we store the encryption key of the previous node in the next node. So when the server decrypts a node, it retrieves two things. First, the address of the previous node, as well as the encryption key of the previous node, or decryption key, whatever. This is symmetric. Right, so this approach of chaining, it will solve both the issues we had with the previous approach. Here we have one key per node. So even if we reveal that key to the server, it's not gonna help the server decrypt the future nodes. Also, for each node, the server doesn't need to talk to the client anymore. Right, so here, for instance, CI sends the blue key over, server decrypts, retrieves the orange key, decrypts, retrieves the green key, and this is how traversal works. There is just one problem because we now do not know how to traverse the list of other clients. Right, so to fix this issue, what we do is that we also store in each node its own decryption key. So see that blue key, which is this decryption key, is stored in the node itself. However, that key is encrypted under this shared master key. So whenever we want the server to traverse the list of other clients, for example, in here, it sends this encrypted brown key to the client. Client decrypts it, sends the brown key over, and then the traversal will start. There is some additional work that is needed to encrypt all these auxiliary data structures, for example, the checkpoints, and there are others as well. But please refer to our paper to see how we encrypt all these additional data structures as well. In the end, we show that if the underlying data structures are linearizable, encryption is secure, then TSD is secure. L secure, where L is the leakage. So this is the leakage of TSD. You don't have to read it, but there are certain things that I want to point out. The first thing is that in the concurrent setting, we have leakage at instruction level instead of at operation level. Right, and this leakage is more fine-grained than what we use in the sequential setting. For TSD, appends do not leak anything, but get operations might leak some correlations with the past operations. But in the sequential case, TSD achieves forward privacy, which was our design goal. In conclusion, in this work, we initiated the study of encrypted data structures, concurrent encrypted data structures. We developed formalisms to design and analyze concurrent encrypted data structures. For instance, we designed what it means to have a secure concurrent EMM, the security definition, and we also developed this new kind of leakage profiles which work at the instruction level and not at the operation level. We also designed TST, which is the first concurrent encrypted multimap scheme. We show that it's linearizable, secure, and it also supports lock-free appends. However, in Git operations, we have to use logs to do some synchronization, but these logs are really fine-grained. So one operation doesn't hold the log for a very, very long amount of time, decreasing the throughput of TSD. And that's all. I'm happy to take questions. Thank you, everyone.
Thank you, Archita. Does anyone have any question for Archita? I have a quick question. So regarding the leakage profile, do you have a sense of, especially because the adversary can schedule the instructions as well, do you have a sense of how much more this leakage would be compared to a sequential setting, like in the
That's
practical?
actually a very, very good question because this is the first work sort of which studies the leakage in the concurrent setting. So we do not really know if, there can be attacks that specifically attack this, adversarial scheduling. But since we did not have that sense because there were no existing attacks, so what we instead did was that we at least aimed for the standard leakage profile from the sequential setting because we know that forward privacy can avoid a lot of injection attacks. So we said that, okay, at least if TST is run sequentially, then you are not leaking more than the sequential setting, or more in the sense more than what is acceptable in the sequential setting. So at least achieve that, and hopefully, um, we will see how this goes and how attacks abuse that adversarial scheduling. Yeah, I don't know. That's a very good question.
Okay, thank you. Uh, if there are no questions, let's thank Archita and our speakers of the session. Thank you. Thank you, Archita. Yeah. So quick announcement. Buses for the river cruise will depart at 5:10 p.m. from the front gate. So hope to see you all over there. Enjoy.